after we've decided that the Matthews correlation coefficient is going to be sort of our, if not only, at least most important metric, you have to basically make sure that it is used as a scoring function for your training. So what you'll do for that is you can go over here and you can use this method, which is use sklearn make score. So you want to import sklearn.metrics. Since you've already imported sklearn.metrics, you have this. But basically, you just have to use it, as you can see here, by basically just writing the name that you want for it, and then you basically write the function here. It's got to be a callable function. So in other words, all you have to do is you have to write MCC is going to be the name of it, and it's going to be make score, and it's going to be the Matthews correlation coefficient is the name of the function, and greater is better is true, because the higher, the closer to 1 it is, the better it is, and that's pretty much it. So you just have to run this like that, and now you have MCC as your score. So over here again, I have a list, empty lists waiting for the scores on each sort of fold. And remember, since this is a repeated stratified k-fold, we have basically 5 splits, and the paper uses 10, but I'm using 5 for speed. And I'm using 2 repeats. So in essence, I'm really doing things 10 times. I'm training the model 10 times on each time on some slightly different set of data. Okay, so I'm going to run this. Okay, so that basically, like I said, we'll go through each regressor, each algorithm will have sort of will be trained sort of 10 times essentially, and then I'm going to basically average the performance over those 10 trials. So I'm going to run this, and although there are many algorithms here, it's not going to really take super long. Let's just go down here, wait for it to finish. So it's done now, and now I'm going to go over here and I'm going to print the mean scores for these things, and it's not in the same order, but let me print it out. And what you're going to see here is that the highest number is the 0.94, and that there's a 90, a 91, and there's a few 89s. So the 89 over here belongs to DT, which is decisions tree, and the champ over here is 94, which is the random forest. The authors of the paper found random forest to be the best one as well. So, you know, this is sort of in line with that. Now, usually in many cases, the sort of more advanced gradient boosting decision tree algorithms like CatBoost, XGBoost, and Light GBM are usually better than random forest. But in this case, you can see the CAT score is 90, nearly 91. LGBM comes in at a decent 91. XGB comes at 89.97, so it's almost a 90. And pretty much everything else isn't really as good, so it seems. But of course, the problem with this is that none of these have been optimized. So this is sort of just like a rough pass. And it basically suggests that we can maybe not deal with Ridge or the K-Neighbors one. I'm not quite as interested in those anyway. So I would rather just sort of compare how random forest does to the GBDTs, and maybe also with a support vector.